guidelines for geophysical investigations in bridge, tunnels, and dams. It is our great privilege, in spite of his busy schedule, he is kind enough to spare some time with us with insights on geophysical investigation to deal with uncertainties in different ground conditions. Please join me in welcoming Dr. Sanjay Rana sir to enrich with us with his profound knowledge. Thank you. Sir, please. So, yeah, please, sir.
So first of all, thank you very much for such generous words. And it's absolutely a pleasure always to be with our young students of geophysics and experienced faculty like yourself. So it's always a pleasure to interact. As I always say, it's a two-way process. In whatever I impart it, from my experience, I also learn in the process of interacting with these young minds who are going to be the future of our country as far as geophysics is concerned. So thank you very much once again, and I'll start my presentation now. My request would be to please note down your questions, or you can put down in the chat box also. I'll take all the questions towards the end of the presentation. So that's the time we can take the questions. Best would be you note it down somewhere, whatever comes in your mind. And in the later stage, you can unmute yourself, and that way more interaction can happen. All right. So with this, I'll start sharing my screen. And
Sure,
yeah. Right. So I hope the screen is visible to everyone.
Yeah, it is visible.
All right. So the topic I've chosen for the presentation today is geophysical investigation to deal with uncertainty in difficult ground conditions. Because whenever we are doing any project, and these days, as you know, that there is a lot of focus on infrastructure in the country. So whenever we are working on infrastructure projects primarily, there is always a factor which we call geological surprises, which all the engineers deal with. And these come from uncertainties in difficult ground conditions. India is one of the country where conditions can be very difficult, in fact, because of, we have young Himalayas, we are working most of the time, and uncertainties can be pretty high in such conditions. So I'll be dealing with that topic today. I represent Parson, which is basically a geophysical company. We are the largest engineering geophysics company in the country. But more than that, we are known for various innovations we have brought in the country from time to time. Our list is already there. I'm not going to read through it. And most recent, of course, has been introduction of BEAM, that is a TBM head monitoring system. And I'll request everyone to please mute themselves, or the co-host can please mute everyone, because there is a noise coming from different sources.
We just
Okay. So BEAM and GPR have been the latest introduction. First made in India GPR, which we launched in 2023, and TBM head monitoring system, which we launched in 2022. Our main strength, of course, is our people who are highly experienced and trained. And we are having offices in Delhi, Jammu, Kolkata, and Bhopal. These are Indian offices, and Bahrain, Saudi Arabia, and Singapore. So we are an Indian multinational, and we are working in more than 14 countries around the world. I have been introduced very liberally already, so I'll not go in much detail of my introduction, except for the fact that I definitely love to work with codes and standards, because codes and standards are backbone of how we can develop technology, how we can develop application of geophysics in a good manner. So I have already authored guidelines on geophysical investigation of dams, tunnels, bridges, and Indian code for subsurface utility mapping. So this is what I have done. I'm also working on number of codes with BIS, Bureau of Indian Standard. Seismic refraction is one, electrical electricity imaging is another. So that's work in progress. All right. Now, coming to the topic of the day, as in the famous words of Shri Visvesvaraya, he said the engineer's first problem in any design situation is to discover what the problem really is. What it may is a very profound statement. And what it means is that before any actual design work begins, it is crucial to conduct a thorough investigation to understand the problem at hand. For example, we are making a dam, we are making a tunnel, we are making any structure on the ground. If we already know what kind of subsurface conditions we are going to meet during the actual excavation, execution, and construction of the project, half of our problems are solved. Because most of the cost overruns, project time overruns actually happen when we meet the conditions which we did not anticipate. So this is something very, very important, very profound statement. Now, if we define investigation, so investigation is a methodology of acquiring advanced knowledge of the site condition so that a techno-commercially viable project layout can be developed. So our idea is that we should have as much knowledge as possible of the site condition so that we can do our design accordingly. The issues which we face today, first is adequacy of investigation of underground project. That is how much investigation should be done. As an example, you're doing a tunnel project. All right. You're doing from point A to B, and let's say the total length of the tunnel is 10 kilometers, right? Now, how much investigation are you going to do? Are you going to do drill holes every 1 kilometer, every 500 meters, every 200 meters, every 100 meters? So, how much is enough? How much is adequate? Second, second is optimum time to be allowed for investigation. There is a tendency to rush into construction because investigation is relatively a very low key affair. One geologist going somewhere on the site, one drilling rig working somewhere, etc., etc. It's not even visible. Whereas when the construction happens, the whole lot of big machinery comes on the site. Media takes note of some construction activity taking. It comes in the newspapers. It comes in practically everywhere. Politicians also come, of course, to cut the ribbon. So whatever is the time allocated for a project, let's say we decide that we'll finish this project in 5 years of time. And if there's some initial delays, we try to squeeze the time of investigation because construction, of course, you can't squeeze much. Investigation, we try to squeeze, and generally investigation doesn't get enough time. Third is the technological improvements required to be brought in, tender condition, standards, etc., etc. That's another big thing. Whenever a new technology comes, there is always a big gap between once we come to know about the technology and when we are able to adopt it. Because in most of the government departments, we have these SOPs, we have the BOQs which are fixed, etc. Next is the cost to be allowed for investigation. Can you take a guess on what kind of money we spend on infrastructure project investigation in India? That is, let's say a project is 100. How much are we spending on investigation? Just take a guess and give me a quick answer in the chat box. Let's see what do you think about it. How much are we spending in India on an average on investigation? So a project is, let's say, 100. So are we spending 5 rupees, or we are spending 1 rupee, or we are spending 10 rupees? What is your guess? Quick chat box, please. We'll keep it interactive. I want to talk to you. So I'm talking to you. Sovik Patra, 1%. Okay. Any more guesses? There are more than 50 participants. I think we need more answers here. 3%. Shubham Yadav, approximately 6 to 8%. Shruti said 3%. 4 to 5. Karthik 0.5. Dheeraj Kumar Singh 15%. 5%. 4 to 5. 5 to 10. 3 point. Wonderful. Thank you. Thank you for your guess on how much we are spending. To be very honest, those who are saying it is more than 3, 5, 7%, my only answer is I wish. I wish it was like that. If we were spending this much of money on investigation, we would have actually got rid of most of the unpleasant surprises what we talk about. Okay. Sorry, 1 minute. All right. Fact is, in India, this is around 0.75%. The average is 0.75%. Globally, it is 3 to 5%. That is the kind of money globally we spend. And India, we are talking of difficult geological conditions. We are talking of Himalayas. We should be close to 5%. We are spending 0.775%. No wonder we keep meeting with a lot of geological surprises and problems. All right, so going forward. Now, when it comes to the adoption of new technology, this is another interesting part. We are still busy working with the technologies which are traditionally available. All right, so something like this. These guys are trying to push this cart with something which is not optimally designed. And then someone comes and says, tools are available, use them, don't be scared, your job is still safe. More often than not, our answer is no thanks, we are too busy. The question we have to ask ourselves is, are we too busy to improve? Whatever new technologies are being offered, resisting to use these new technology basically means that we are not working at our full potential. We are not working with the same efficiency which we are capable of. Fact is that good quality of investigation, good quantity of investigation, and good time allowed for investigation leads to less uncertainties and less cost and claims. This is a globally established fact that better are your investigations, better is your project execution. And by saving very little money in investigation, you actually pay a very heavy price at the time of construction. When cost of the project increases, the time of the project increases when you meet with these geological surprises. So what are these geological surprises? Fact is that first of all, what is a geological surprise? Just to put a perspective, you're doing a tunnel and you come across a shear zone or a aquifer, and your tunneling stops completely, right? Maybe your TBM is flooded, maybe it is buried. In many projects, it has happened that TBM has got buried under the ground, right? Fact is that expertise and engineering solutions are available for dealing with almost any ground condition. Again, going to the same example. Let's say you're going for tunneling, you come across a shear zone. Now you can simply do a pre-grouting or pre-consolidation and go through the shear zone without any problem. So expertise and solutions are available provided we know about existence of these kind of geological conditions. So the problem is meeting the unexpected or uncertainty of the ground condition. So as I always say, a geological surprise is nothing but a condition which you did not anticipate because you did not investigate. As simple as that. That is the statement which I always make, that this is a condition which you meet because you did not anticipate it, since you did not investigate it. Now, what are the challenges we have in the underground? Look at this particular figure. This is from ITA, International Tunneling Association. And it says, even a comprehensive exploration program recovers a relatively minuscule drill core volume that is less than 0.0005% of the future excavated volume of the tunnel. Look at this figure, 0.0005%. This is the kind of information we are having based on which we are finalizing our design. And this is the case when comprehensive exploration program has been conducted. What does it mean is something around 5% has been spent in investigation. In our case, we are spending 0.75%. So you just add one more zero to this figure. So the information we will have is 0.0005%. That is the kind of information based on which we are taking our decisions. Now, can we call ourselves a smart decision maker, or we actually are decision maker which are practically taking all the decisions with our eyes closed, right? So this is the kind of information which is available to us, which is not adequate to make good designs and take good decisions. Now, as an example of what I'm saying, let me just take you further to an interesting question. Let's say we wrap a rope around the earth. We know the radius of earth, okay, close to 6,400 kilometers, all right, 100, 200 kilometers this way and that way, pole, equator, and all that, right? So let's say we wrap a rope around the earth. If we increase length of the rope by 6 meters only, how far above the earth's surface will the rope be? I hope you understand the question. I wrap this rope around the Earth's surface, okay, and then I increase the length of this rope by 6 meters. My question is now, with this increased length, how far this rope will be above the Earth's surface? Quickly, your answers in the chat box, please. Let's have your answers. Let's have your answers in the chat box. What do you think? What do you think? Shubham Yadav is saying 6 meters. Okay. Let's have more answers. Did you understand my question? I wrapped a rope around the Earth's surface, and then I'm saying if I increase the length by 6 meters, how far above it will be? Okay. One answer I'm having is negligible. The one is saying 0.00005%. Shashant Raj Mishra is saying almost 0.99 meters. Depends on diameter of the rope. No, diameter is insignificant. Take it as negligible diameter. It will depend on circumference. Circumference you can calculate. It's 2 pi r. It's very less in thousand. Dheeraj Kumar Singh. All right. So majority of the answers which I have is negligible. It's very less in thousands. Okay. So all of you did not read the top part of this slide, which says always measure and calculate. Don't assume and guess. You made a guess. And when you make a guess that, oh, it's 2 pi r, and r is 6,400 kilometers. So that's the length of the rope. If I just increase by 6 meters, how much difference will it make? How much difference will it make is like this. If you calculate, the new radius is 2 pi r dash is 2 pi r plus 6. R dash minus r is 6 divided by 2 pi. It is 0.955 meters or 1 meter. That is the answer if you calculate it. Amazing, right? Say yes if it is amazing in the chat box. Just write yes if you find it amazing. Is it amazing? It is amazing, right? That's the value of calculating rather than guessing. Whereas in most of the investigation works, we are making a guess. We find the rock here, and then we make a guess, what we call interpolation, that in between also rock is connected by a straight line from here to there. Another very interesting question in that case. Let's say if I take a paper and fold it in the middle. I take a paper and fold it in the middle like this. Okay, one fold. I fold it again, two folds. I fold it again, three folds. And like this, I keep folding it for 50 times. What would be the thickness of my paper bundle? I want a quick guess on this. What would be the thickness of my paper bundle? 1 meter, 2 meter, as thick as my room, as thick as the Statue of Unity? Just some kind of approximate thickness, what you can think of. 50 centimeters. Okay. Let's go. There are too many participants. And I'm not going to spell out the names. Type whatever comes to your mind. Yes, it's very difficult to fold more than 8 times. Understood. But we are assuming this as a question only. Okay. Okay. All right. Here I'm getting few good answers. Okay. All right. Yeah, don't try to do it. You can't fold more than 8 to 9 times. Okay. Here I'm getting few good answers. But like few answers are 50 times the thickness. You are basically ignoring that once you fold it, let's say it's 0.1 mm. Once you fold it, it will become 0.2 mm. Again, it will become 0.4, then 0.8, then 1.6. Like this, it will keep increasing. Okay. And the real answer is, after folding a piece of paper 50 times, the thickness will be 112,589,990,684 meters. It is many times greater than the distance from Earth to Moon. All right. But whenever I ask this question just like this, people say, oh, few meters, 1 meter or something like that. All right. So this is the importance of doing your calculation. Always measure and calculate. Don't assume and guess. Okay. So be a smart decision maker, not a blind decision maker. So the next question is, how much should we be investigating? Like, as we have seen in this lecture till now, that less investigation is not a great idea. So we should investigate more. Then how much should we investigate? Should we be doing drilling every 1 meter, every zero 0.5 meters, every 2 meters, every 5 meters? Fact is, that's not feasible. That's not technically feasible. That's not economically viable. We cannot convert ground into Swiss cheese as we talk about. So what is the answer? And that answer comes in terms of geophysical investigations. Since all of you comes from the geophysics background, thankfully I can very well skip this particular introduction part on geophysics. But even if you have to go out and talk to some non-geophysicists, it will come in handy. If you compare geophysics with medical imaging, that is, in medical imaging, we are sending different kind of rays and waves inside the human body, trying to find out what's inside the human body without cutting it open, without doing any surgery. Similarly, in geophysics, we are sending different kind of rays and waves inside the earth to find out what's inside the earth. Here, we are not only sending rays and waves, we are also measuring naturally occurring fields like magnetic field, gravity field, etc., etc. So that's a very, very good, analogy to explain geophysics to engineers or non-geophysicists. Okay. And of course, as a science, it is at the intersection of geology, physics, and maths and computer science. So why to use it? All this what we have discussed till now, the basic reason is, first of all, low cost. It is the same comparison as between X-ray and surgery, all right? So it's low cost, rapid coverage. Today with heliborne methods, for example, you can do hundreds and thousands of kilometers in a day. So it's very rapid. Next is continuous information. Continuous information is one of the most important part. That is, let's assume this kind of a scenario. I'll again request everyone to please keep themselves muted. Okay. So let's assume this kind of a scenario. This is a limestone pinnacle. This is a void. And here we have few anthropological features. Now, what are the chances that drilling will actually find out presence of these localized features? Chances are 1 in 1,000 or 1 in million, depending on spacing between your drill holes and size of these objects, right? Whereas if you do a geophysical campaign, you are able to map all these features in a continuous manner. So continuous information is one of the biggest reasons. Optimization of drill holes. No geophysicist should ever claim that by doing geophysics, we are eliminating drilling. We are not eliminating drilling, because geophysics is giving you physical properties. It can give you P wave velocity, shear wave velocity. It can give you resistivity, conductivity, magnetic susceptibility, density, etc., etc. But there are so many parameters which have to be measured on the real samples which are taken out, C values, phi value, etc., etc. Plus, geological translation of physical value is needed. For that, you need drill holes. But instead of doing drill holes in a particular pattern that every 50 meters, 100 meters, etc., etc., you can optimize your drill holes to be done based on the results of geophysics. And of course, it leads to minimization of surprises, because as I said, surprise is a condition which we did not anticipate because we did not investigate. Once you have done a proper continuous investigation, your surprises are minimized. And it's good to use in the early stage before design of the project for better planning and smooth execution. Unfortunately, even today, we are using geophysics more as a firefighting device, except oil and gas. Oil and gas, definitely no drilling is done unless some geophysical data has been taken in the area and we have found some favorable structure. But mostly in the field of engineering and even mining, we are using it sometimes with drilling, after drilling, mostly in the firefighting manner, which is the worst way of using geophysics. Then, another mistake which we make in using geophysics is not to use it correctly. When we say correctly, There is a 7-step framework of geophysics. We'll start with setup. Setup establishes the objectives, consider conventional practices, and identify how geophysics might contribute. Then we go to finding out between the host and the target, where are we going to get maximum contrast? Okay. Which physical property will give us the best contrast? Then we go to the survey design. In survey design, we consider everything, possible source of errors, noise, misinterpretation, etc. We decide the grid pattern, we decide the line spacing, and then we go to data collection. More often than not, we are jumping directly to data collection in most of the projects. We get a mandate from the client, we take our equipment, go to the site and start data collection without seeing what is the geology of the area, which physical property contrast will be there, what should be my grid spacing, what should be my line spacing, etc., etc. Then of course comes processing, then interpretation, and then synthesis. That is, combine this interpretation with prior knowledge about the problem, other relevant information, borehole data, if available, etc., etc. And never hesitate to also suggest a follow-up investigation program if required. Certain areas you might find an anomaly, and you might then recommend a borehole, a drill hole in that area to confirm that anomaly. So this is the 7-step framework of geophysics, which more often than not is not followed, which results in failure of the geophysical programs. Which method you are using is very important. Using a wrong method for a wrong objective can result in the failure. And remember, most of the clients who are engineers are really not aware of intricacies of the geophysical methods. They trust you. They will go with your suggestion, your advice. All right. So it's very important that you choose the method correctly based on shape of the feature, physical properties, contrast, penetration depth, resolution required, etc., etc. Important, very, very important thing. Then coming to advantages and limitations. Advantages we have already discussed: rapid, cheap, non-destructive. And limitations, of course, it can be ambiguous without controls, poor discrimination in some cases, noise and artifacts during inversion. So there Achal Jaiswal. I gave you the co-host Achal yesterday. I'm sorry, but now in the meeting I won't be able to do that. Okay, but I made you the co-host yesterday, so I'm sorry. But if there's anything you write in the chat box, I'll do it as a host. I will do the multiple jobs. Okay. And depending on which property you are looking for, there are different methods. For example, you are looking for strength parameters. Okay. Now, once you're looking for strength parameters, you are looking at seismic methods. Okay, because there you are able to measure P wave velocity, S wave velocity, shear wave velocity, etc., etc., and even surface wave velocity, right? When we are talking of contrast in conductivity or resistivity, you will go for resistivity or EM methods, right? So depending on what is the property contrast, you choose one or more method. Generally, never one, but couple of methods based on the property contrast. So now I'll take you through 6 or 7 different type of methods. It will be not like a big lecture in geophysics because that you are already attending in your institute. I'm going to take you certain case studies, certain examples to give you the importance of how these methods can be used. Okay. First is infrastructure project site investigation. So this is where we are starting from. What all methods are useful in that? So first, where does geophysics falls? See, no technology is complete in itself. It's part of a process. So where does geophysics fit in? Necessary investigation steps for any project start with geology. Available geological maps you study, you look at the satellite images, you conduct a geological mapping where a geologist actually goes to the site, does the geological mapping, and then comes geophysical investigations. Okay. But mandatorily, they should come before drilling. Unfortunately, today, most of the time rather, we directly jump to drilling. and we do geophysics only at few areas as a complementary study tool or a firefighting tool. That's the worst way of using this technology. It should be done before drilling, and based on the results of geophysics, drill holes should be optimized and drilled. And then other studies, hydrogeological, seismicity, etc., etc. Okay. All right. Now, when we talk about engineering geophysics, okay, let's have a quick, again, a quick quiz, not quiz, Paul. Uh, I've been talking for last 15-20 minutes now. How are you enjoying it? On a scale of 1 to 5, if you are loving it, type 5 in your chat box. If you're finding it very boring, type 1. Let me also have some feedback. Oh, you're a wonderful audience. My God. Few of you have made your own scale also. All right. Because I got few
Sir,
10s.
Sir, sorry to interrupt. Just I have one urgent work, so please permit me to.
No problems. Please carry on.
Okay. Thank you.
All right. So thank you very much. You have your wonderful audience. As I understand, you're enjoying it. Most of you are enjoying it a lot. Few of you are not enjoying it so much, but that's all right. I'll try to keep it interesting as we go ahead. Now, engineering geophysics is not only near surface, because if you sometimes search for engineering geophysics or near surface geophysics, even in Wikipedia, they say it looks into the first tens of meters of the subsurface. Now, when we are doing tunnels, which are going as deep as two kilometers, that overburden is up to 2 kilometers, how can engineering geophysics be shallow? All right. So it is not only shallow. For example, Helibond time domain electromagnetic. One method which I would like to talk about. It is time domain electromagnetic. So we are again using the principle of electromagnetics. We have a loop, transmitter loop, and EM fields are being generated. They're going into the earth wherever conductive bodies are there. Secondary fields are being generated, received in the loop, and ultimately we are making a conductivity or profile of the subsurface. Now, it works like this. Okay. So this way, this loop is going all over and we are recording the data. Okay, it is being used for geotechnical. In India itself, it has been used for tunnel route studies. It has been used for groundwater exploration, and you can do up to 1,000 kilometers in a single day. Okay, this is how time domain electromagnetic is working. Best thing is the data sampling is very fast. You are having very good data. You are flying number of lines in almost 3D pattern. You can combine all the data and practically make a 3D volume of your subsurface, which gives you a very detailed idea of what's happening inside. Now, if you look at it, this is the kind of interpreted, that kind of profile which you get. This is the top terrain. You can see the terrain. And this is around 600 meters. So this is 800-meter mark here, 0 here. So at any point, the slice thickness is around 600 meters. So using time domain electromagnetic, we are seeing up to around 600 meters in the ground. And imagine you had a tunnel going like this at elevation 400 meter. Okay. Now, this is conductivity. Now, you already know that higher conductivity is bad news for us. Low conductivity is good news for us in the earth material, because earth material by themselves are insulators. They become conductor only when moisture or water is there, except the mineralogical part of it. Now, once you take it, now you know you are going to meet a small weak zone here, you are going to meet a weak zone here, and then you're going fine, and then you're going to meet a weak zone here. So now, even before you go for your tunneling, you already know where your problems are, and you have a depth of investigation of, let's say, 600 to 700 meters. So it's just not near surface. Next very interesting method which I talk about is passive seismic tomography. This is the method which we have used in India for oil and gas exploration, both for Oil India Limited and for ONGC. We are yet to use it for engineering application. But in this, what we are doing is we are listening to these earthquakes which are coming under the surface all the time. And we are recording earthquakes of magnitude 4 and less. Generally, the one which we feel are much higher magnitude. We are not interested in these earthquakes because we are more interested in point source. If the earthquake is very large, it doesn't resemble a point source anymore. So we are recording these earthquakes by putting these 3D three component sensors on the surface. It's a continuous recording. And then we are picking the P wave and S wave arrival times. And based on that, we are making a velocity model of the subsurface. And this velocity model, as you can see, around 2.4 kilometers. So it's minus 1.2 to 1.2 kilometers. And this is the P wave velocity distribution in this particular area. So it is no more just near few hundreds or a few hundreds meters. We are able to penetrate much deeper than that. Now coming to seismic methods. Seismic methods are, there are various seismic methods. For example, you have seismic refraction, reflection, MASW, refraction microtremor, crosshole, downhole, seismic tomography. And they are all based on, for example, refraction is based on P wave. Although S wave refraction is also possible. I did it in India in 1997. That was the first shear wave refraction which was done in the country. And that time MASW was not at all practiced. And that's why whenever we wanted shear wave velocity, we had to do shear wave refraction. Now MASW has practically replaced it. So refraction is more confined to P waves. Then seismic reflection. Okay, this is working on the refraction principle. It is working on the reflection principle. MASW or REMI, surface waves, crosshole, P waves and S waves, downhole, P wave and S wave. Here SV is the main component, here SH is the main component, and then seismic tomography. So these are different seismic methods. I'm not going in detail of all the methods. I'll just show you examples of few. So, okay. Sorry. So here we are starting a seismic source on the surface. We are having these wave fronts, showing them as rays, and they are getting reflected, they are getting refracted. And as per the Snell's law, sin I upon sin R is V1 upon V2. So if V2 is greater than V1, at R is greater than I, at one particular incidence angle, R become 90 degrees. Yes, 90 degrees. And we have this critically refracted ray path, head waves coming on the surface. No theory, as I promised. And this is how we are doing the whole thing. So in refraction, we are making use of refraction property of the seismic waves. So of course, geophone planting has to be done. Geophone, geo is earth, phone is listening device. So it can be through spikes, metal base. We connect these to a multi-core cable, and then we record the data. This also can be done in water, all right? So because you are already studying seismic refraction, so you must have studied all the part about land, but it also can be done in the water. Geophone is replaced by hydrophone, and energy source is replaced by either an explosive or an air gun. So this is my own project in River Godavari, where we did refraction across water. These are recorded data. So as this will be your different channels. This is a 24 channel system, and here will be your time. So wherever your shot is, time will be least there. It will keep increasing, and then you do the interpretation ultimately to find out a velocity model, something like this. Okay. So and as I said, it will give you the physical property in terms of P wave velocity. So this is, for example, now you will translate it into geology based on your experience, but more than experience, it should be correlated with some drill hole data in the area. So this will be a top overburden, this is more compacted overburden, this will be weathered rock, and this will be the rock interface. And as you can see, it will show you the complete topography of rock. Wherever the undulations are, even if the deepening of rock is taking place, it will beautifully bring it out, right? So continuous information. Now you are no more depending on interpolation, but continuous information. And even small features like a shear zone. Okay, this is just to 7 to 10 meters wide shear zone, beautifully found out by seismic, and this is seismic refraction tomography, right? Earlier layer-based seismic refraction had definitely limitations in these kind of situations, which tomography has been able to overcome. This is a very good example of practical application. So this was a tunnel project where few drill holes were done, and based on these holes, this was the geological model which was developed. And as per this geological model, here we were having, some what you call it, weak layers, but in between, this was all going to be good rock. Okay, no problem. But when the refraction tomography was done, as you can see, this is the weak part. But even in this part, there are going to be few zones which are having low velocity. And these would have been encountered during tunneling as what we call geological surprises, if investigation was not done. So that's the importance of these kind of investigations. So it gives you bedrock profile, rock quality and depth, thickness of overburden, fracture and weak zones, slope stability studies, and there are limitations. Velocity increase with depth is mandatory. Velocity contrast is mandatory. So every method will have its own strength and weaknesses. Okay. And P-wave velocity, we all know, is a good indicator of the strength of the material. That is, more strong the material is in terms of mechanical property, higher is going to be the P-wave velocity. So here comes a quiz. Which of the following material will have highest P-wave velocity? Air, dry sand, water, or basalt? A, B, C, or D? Just give me your answer in the chat box. A, B, or C, or D? Just type your answer in the chat box. Right, great. Thank you. So all correct answers. So now we know that if we have to categorize a site based on strength, we can go for seismic refraction. Okay. So basalt is the correct answer. Thank you very much. Thank you. Second method which we talk about is MASW or REMI. Now in this, as arrival time of seismic waves, we know we have P waves coming first, then comes the S waves. Both of these are body waves, and then comes the surface waves. All right. So this is the surface waves. Now, why shear wave velocities are so important? Because look at this table. Number of materials like saturated gravels, clean and dirty, clay deposits, weather rock, coal, and even quicksand can have the same P wave velocity, 1500 meter per second. From any construction or foundation point of view, I hope you can understand the difference between quicksand and any other formation. Quicksand is where you can't even stand. It has no shear strength. So if we measure shear wave velocity also, it gives a more unique definition of the material. So quicksand, for example, will have a shear wave velocity of 0. It doesn't, shear waves do not even travel through what you call it, water, liquid, or air. So this is why it's so important to measure shear wave velocity. In this case, it is done based on the Rayleigh wave dispersion curve. So we do the acquisition, make the dispersion curve, do the extraction of dispersion curve. At the end of it, we have this profile of the subsurface. Okay. And once we put number of these profiles together, we can make a 2D image of the subsurface. So this is, for example, depth, and this is your bedrock. And here you can see these are the areas with low shear wave velocity. Number of examples. This is a good example from Statue of Unity, which we did. And you can see the complete topography of different layers. Very, very good information. And then you can use empirical formula to change it into site classification, n-value distribution, allowable bearing capacity, shear modulus, etc. But these are all based on empirical relationship. What you're measuring is the shear wave velocity. And this is a good example of interpretation of the data. That is, you have the data. This is a GPR data. This is the MASW data. And then you do the joint interpretation based on your understanding of geology, which generally comes from some drill hole data available there. So this is red soil, weathered rock, fresh rock. So like this, you're able to do it. And then there is a classification for earthquake site response studies, which tells you different kind of rocks, what kind of shear wave velocity they have, and ground shaking amplification, how it will change for different type of shear wave velocity. That's why in most of the what you call it uh, studies of earthquake site response, VS30 is a parameter which is always used by designers. Okay. So it is used for various applications like faults, folds, S-wave velocity, then buried pipelines, foundation, bedrock mapping, etc., etc. There are many applications. Then we come to seismic tomography. So in seismic method, we have talked about refraction, we talked about MASW. Now, in certain both these methods are surface methods. So you are doing from surface, and as you are going down, your resolution is obviously getting compromised, like any other geophysical method. Sometimes we need high resolution information even at the deeper part, and that's where seismic tomography comes in picture. In this, we are having a borehole transmitter, we are having borehole receiver, and ultimately we are creating a very big crisscrossing of seismic waves between your transmitter and receiver. And after that, we are going for inversion. And once we invert, we are getting a good definition of subsurface in a very high resolution manner. Now, this resolution, of course, is dependent on the spacing between your transmitters and receivers, but it is much higher than any surface method can deliver you. Okay. So this is used for various applications. Now, this is one good example of dam. So here you have a dam. This is the top of the dam, and this is the gallery of the dam. And seismic refraction has been done between the top and the gallery. Sorry, tomography has been done between top and the gallery. So here hammer has been used to initiate the seismic waves. Here geophones have been used to receive the seismic waves. So these are kind of crisscrossing. And once you invert the data, do the processing, you get the complete P-wave velocity distribution inside the dam body. And now you know where are the weak zones. Wherever low P-wave velocity is being observed, these are the weak zones which has developed because of leaching of material, because of flow of water over a period of time. So that is the strength of these techniques. Similarly, cross-face between upstream and downstream of a dam can do the same thing. And look at this example. Here, 5 drill holes are there. Rather than interpolating information between the drill holes, tomography has been done. And this fault here has been delineated based on seismic tomography. So this is again a very interesting method, very powerful method for this. This is one of my favorite projects we did in Bhutan. This is the deepest seismic tomography reported, at least in the world till date. Our boreholes were 250 meters deep. At one point, the distance between borehole was as much as 115 meters. And it was to delineate a cavity which had developed because of a fall, chimney formation in the tunnel. And you can see this cavity definition very clear. This was the rock line. This is a top overburden, rock line, and then this was a cavity which was created. At one point, the cavity was as much as 85 meters by 60 meters. So a very strong technique for high resolution subsurface. Okay, another quiz. Which wave caused by the earthquake caused maximum damage and destruction on Earth's surface? P wave, S waves, distortional waves, or surface wave? A, B, C, or D? Let me have your answers in the chat box. Good. Thank you. So everyone has got the answer right. It is the surface waves that cause the maximum destruction. Wonderful. Thank you. That's the best part of making presentation to IIT, ISM students. All right. The next method I'm going to talk about is electrical resistivity imaging or tomography. So like in seismic, we were using these acoustic waves. Here we are using electrical current. So there we were looking more in the strength of the strata. Here we are looking at conductivity or resistivity of the strata. Different formations have different range of resistivities, but remember, range of resistivities. So just by having a resistivity value, you cannot classify a formation. Okay. So here we use a resistivity meter, energy source, electrodes, and connecting cables. Process, I will not go much in detail because you are already students of the subject, but basic law is the Ohm's law. R is equal to V upon I multiplied by geometric factor, you get resistivity. What has changed from the 4-electrode method to date is basically resistivity imaging, when we are using number of electrodes to create a 2D or 3D image of the subsurface. And this is a good example of the kind of resolution you can get. This is, you can see 1060, 860, so 200 meter is the scale here. And this was to detect a shear zone in a tunneling project. Okay. Now, this was a beautiful example of a cavity which was detected in one of the project using imaging. This is a good example of why we should combine methods. You see, in this particular project, there was seismic refraction which was done. Seismic refraction will not find out a zone of low velocity under the rock, which can happen in the case of folding. ERI did that. And that's why it's always advisable to combine methods. This also can be done in water. So this is a river Karnali in Nepal, where we put the electrodes and we did this electrical resistivity imaging across river water. These days, much more advanced system have come. That time we didn't have these advanced system. It was 2001. So we made this rope arrangement and all that. But these days you can have this entire string with a boat and you can do very quickly electrical imaging of the subsurface. This is the strength of all this. This was a particular project in which they had done number of boreholes and they had established this as the rock line. This yellow one which you see, this was established as a rock line. And it was established something like this. And they were almost ready to start a construction, excavation, taking this as a dam site. We were asked to do this investigation and we came across this shear zone sitting right across the proposed dam axis. And of course, this saved a lot of time, money, and surprises at the time of construction. Data also can be presented almost in a 3D manner. So this was a project in Kota, where a cavity was detected when drilling was being done. Drill rig went 60 centimeter down. This was the cavity, and this 3D image is showing this is the water table, all this blue. And as you cut from one point to the other, you are able to see the cavity extension in which direction it is going. So you are able to see it very nicely that how the cavity is propagating from one end to the other. So that's what we say, visualization of data has become much better with time, with more computing power. So this was a cavity. Okay. Then GPR, ground penetrating radar, one of the very hot topics in geophysics. It didn't exist when I graduated. I never studied GPR. So, but it has come in 90s and now it's a very popular method. We are working with the principle of electromagnetic reflection, EM wave reflection, sending these EM waves inside the ground, which are getting reflected from any interface across which there is a change in dielectric constant. Number of scans to put together, we have a B scan. And once we put the whole thing in 3D, we have a C scan. Okay. So this is an example of underground pipes. You can use it a lot these days for concrete scanning. So these are beautiful examples of rebar mapping using rebar and conduit mapping using GPR. So this is a one big application area where you can do the 3D mapping and cut slices as if you are taking a piece of butter and cutting it at different depth. Like this, you can keep a this shows depth here. So it is, let's say, 0.3 centimeter, then 0.5 centimeter. Like this, you can keep cutting at different depth and see how the subsurface is behaving at these depths. It can be also used for for tunnel studies to find out defects behind lining, etc. Number of applications. This application is very interesting, where a metro pillar was there. A crack was developed in a metro pillar, and the client and contractor obviously were fighting with each other. Contractor said it's just a superficial crack. Client said, I don't believe you. Maybe there is a problem inside. And so GPR was done. So you can see this GPR being done in all the parts of the pillar. And ultimately, sitting here at a depth of around 71 centimeter, the defect was found. So very, very good application in these kind of things. Lastly, I come to a few unique applications. For example, I have been using a simple seismograph to find out pipeline leak detection, for doing pipeline leak detection. Whenever some leakage is there, a noise is created, and if you put your geophone over the pipeline, you can detect this noise and ultimately find out where exactly the leakage is taking place from. I have used GPR also for pipeline leak detection. In Bangalore, a lot of work was done. So this was high amplitude reflection from saturated layer top. This was loss of signal due to increased conductivity. There can be 6 to 7 different kind of signatures in GPR based on change in the water saturation level, depending on the soil property. So it's not only one kind of signature you will get. This is another very good example where concrete slabs were there. Behind these slabs, few cavities had developed because of water seepage. This is a man here. So you can imagine how big these slabs are, I think 22 meters. And then investigation was done to find out what is the extent of cavity. So these are depth slices, 0 to 9 centimeter, 8 to 17, 16 to 25. And you can see how the cavity is, where it is starting, up to what depth it is going in the depth slices. Same thing you can make as a 3D volume to have a more detailed study. Sometime in the existing tunnels, there is a seepage that is taking place, and we want to find out where it is coming from so that we can do the rehabilitation. Now, electrical current doesn't understand gravity, so we have put electrodes on the top of the tunnel for the investigation, and we get this image. Seepage was coming from here. Common sense says that we start grouting from here, but nothing will happen because this is a very compact formation. Actually, bad zone was here, and water was taking this route. So this is the application of ERI even in the existing tunnels to find the seepage paths. Coming to end of the presentation, in many cases, geophysical surveys we are reported it didn't work, it failed. What are the main reasons? First is inadequate planning and survey design. As I said, 7 step of geophysics, right? Sometimes we directly jump to data acquisition. That's one reason. Wrong tool selection. So using a kitchen knife to shave, you are almost certain to have a cut, right? So if you choose, for example, electrical resistivity to find out the strength of the material, that's a problem. Or you use seismic refraction to find out a buried pipe, well, that's a problem, right? Method lacking desired resolution, geology ignored, only single tool used. Different formations, totally different formations can have a similar physical property. So always use multiple tools to uniquely identify your problem. Then technological failures, data processing and interpretation errors, these all lead to failures. To conclude, why use geophysics? We started from low cost, rapid coverage, continuous information, optimization of drill holes, minimization of surprises, saves huge cost towards change plans, project delays when surprises crop up, and good for early stage application. Where all you can use it? Since 95, when I started working as an entrepreneur after leaving my job from atomic energy, I have been only thinking, where can I use it, right? Now it's your turn to start thinking, where can you use it? And only limit is your own imagination. Wherever you come across a problem of the subsurface, you can use it. Now, a parting gift for all of you. Here is a small QR code. Take out your phones, scan this QR code. You will be asked for your name and email ID, I think. I'll just do it with you. Okay, so I'll just scan it. And yeah, it asks for your name. So I just put my name. It asks for your email ID. So I put my email ID. It asks for your mobile number. These are mandatory fields, and then organization and designation are optional. Just press submit, and in next 10 seconds, you will receive a very good document, which is guidelines on geophysical investigation of tunnels. Although it writes tunnels, but this document practically covers all the methods which I have discussed here. And second, advanced geophysical techniques for rapid subsurface investigation for civil projects. So these two you will get within 10 seconds on your mobile. So just scan this code and get these documents immediately. All right, done. Have you scanned it? Can I go to the next slide? All right. So that's it. Thank you. And this is my email ID, sanjay@parson.biz. So for anything, you feel free to write to me. Calling is a problem. I generally am not able to take calls because I travel a lot. But email, I generally reply within 24 hours. So thank you for your attention and feel free to write to me anytime. I'll stop sharing my screen now. Okay. All right. So now I'll take questions. First question is from Shruti. How can we use geophysical surveys in real-time tunnel construction? Very good question, Shruti. See, whenever we talk of investigation, we always talk about different phases of investigation. So first was tunnel route alignment. So you can use this time domain electromagnetic, helibone, and passive seismic tomography to find the good route for your tunnel investigation. That's number one. Then you can do surface geophysical investigations like ERI, seismic refraction, etc. to further get more high resolution data of your tunnel route. Now you're talking of the real-time tunnel construction. So real-time tunnel construction, when we are doing, there are two methods which are being used primarily. One is TSP, that is tunnel seismic prediction, which is done from the face of the tunnel, and it gives you an idea of what is coming ahead of the tunnel. And second is beam. Okay, that is the electrical method, which again it is done from the face of the tunnel, and it gives you an idea of what is coming ahead of you. One gives idea based on the principle of seismic reflection, and second one is doing on the based on the principle of uh, IP and focus electrical current. Okay, I hope I answered your question.
Hello, sir.
Yes, Ayush, please go ahead.
Sir, you have it was a very nice talk, and you have mentioned that there was resistivity methods going in the river and the water.
Right.
Can you please give explain how to do resistivity method?
See, as I said, these days it has developed a lot. Now you're having these cables which can be completely submerged in the water. And in our time, our cables were not submersible, so we actually had suspended electrodes in the water. But these days, you can have this submersible cable, and you can put them in the water, even on the top surface, maybe just few centimeters down from your top, or in the bottom. And of course, it will work mostly in the cases when the water is the river water or reservoir water, not the sea water, because then the conductivity is very low, then it's a problem. But otherwise in river water, when the resistivity can be as high as 100 ohm meters, it just works as another geological formation, and you get very good results from there. Okay. Now, then there's a question from Mr. Aman Sharma. What are the reasons behind skipping geophysical investigation in modern projects, even though it can save a lot of money, time, and even lives of people? Lack of awareness is the first reason which I'll talk about, okay? Because if you look at it, geophysicists are in minority, okay? We are very few of us. And that too, most of the geophysicists generally are into oil and gas sector, right? So in engineering applications, there are very few geophysicists. So the lack of awareness is there, that people do not know about these methods. The engineers are not aware how much they can really get benefited by use of these methods. So lack of awareness is one. Then secondly, of course, is a blockage is that we are very comfortable working with our traditional way of working. As I showed you the first first cartoon, we are trying to pull a cart without a wheel, and someone comes and says that, tools are available. First, we are not very sure of what this tool will do for us. We also are scared that we might lose our job because of this, because we don't know how to use this tool. Okay, so someone else will become more powerful who has the knowledge of this tool, right? So there are a lot of issues. Like when the computers came, there was a lot of resistance about computers. Everyone said that computers will take away human jobs. Now AI is coming, and again there is a lot of resistance towards AI. So resistance towards the new technology. That's the primary reason. Okay. Then Shubham Yadav, by considering the dynamic nature of ground condition, how do we stay updated with the latest advancement and ensure our method remains effective over time? By considering the dynamic nature of ground conditions, how do we stay updated with the latest advancement and ensure our method? To be very honest, these two slightly different things. First is how to stay updated on the latest advancement, right? That's one part of it. So you should be updated on the latest advancement, and the only way to do that is to really follow what's happening in the world in your field. And I find journals as the best way of doing that, right? So keep looking at the journals. What are the new techniques coming? What are the new application areas opening up? What people are doing around in the world? So that's something which I will do uh, to keep updated. As for the ground conditions are concerned, the ground conditions are changing from point A to point B, and that's why whenever you are planning your survey, you need to consider what kind of geology you are working with. Are there any specific properties of the site which you need to consider, and then design your survey accordingly. I hope I answered your question. Okay. Thank you, Shruti, for your compliment. Thank you. It's nice that you liked the lecture. Okay, then Aman is saying, sir, you told that P-wave velocities can be same in different geological environment, but in the quiz, maximum P-wave velocity was found in basalt. Is this statement not contrary? No, it is not contrary. When I give you a choice, all right, I said out of these four material, which material will have highest P-wave velocity? I did not say that which material in the nature has the highest P-wave velocity. I said out of water, air, sand, and basalt, which will have the highest P-wave velocity. So there's only one choice in that, and that's basalt. Right, Aman? I hope it's okay with you.
So I have a one doubt. Uh, as the recent advancements, when we predict the soil characteristics, when we estimate the soil properties during the construction of any of the building, most of the times the civil engineers, why they prefer the testing or experimental methods over what we have different like downhole area measurements. There are the many different methods that by analyzing strong motion records. So what is the reason behind this? Is that the reason mainly that you mentioned about the adopting a new technology? Or is this just something like the results what we get from the new methods are quite unrelatable?
See, since you are a student of the same discipline, you also know that reliability and accuracy of the methods, how it has improved over a period of time, and how we are trying to bring uniqueness from non-uniqueness by combining different methods and using the integrated approach. 99.99% the reason for less use of these methods is lack of comfort of using these methods by engineers. They are definitely not comfortable. They don't understand the methods so well. And we as geophysicists do not make too much of effort in making them understand the methods. That is where the problem is. Earlier geophysical reports were actually written in a way which only a geophysicist can read. Now that's where the problem is. We have to make our results in such a way that engineers, geologists, and a non-geophysicist should be able to understand our results properly. Then only this gap will vanish.
Thank you, sir. Thank you for your response. It's a
Thank you, sir, to your kind words. Yeah, it was very nice to talk with you. Now I invite Professor Niptika Jana ma'am to give a vote of thanks.
Good evening, sir. Thank you so much. And I stand here with immense gratitude and honor to extend my heartfelt thanks to all of you for making today's webinar by Dr. Sanjay Rana a resounding success. We are truly privileged to have had the opportunity to gain insights and knowledge from such a distinguished expert in the field of geophysics. Dr. Rana's presentation was not only informative, but also inspiring, providing us with valuable perspectives on the latest advancements in applied geophysics. His vast experience and profound expertise have undoubtedly enriched our understanding of the subject. I would also like to thank all the faculty members, guests, and participants for your active participation and engagement throughout the session. Your enthusiasm has contributed significantly to the success of this event. And as we conclude this enlightening webinar, we look forward to more opportunities for collaboration and knowledge sharing. It was our earnest desire to invite Dr. Sanjay Rana to visit our department in the near future, allowing us to benefit further from his expertise and insights. Once again, thank you all for your presence and active participation. We hope to continue fostering such enriching academic interactions in the days to come. Thank you so much, sir. Thank you so much.
Thank you so much. Thank you, everyone, for this wonderful interaction. And I really look forward to coming to your institute and interacting more with you. Thank you.
That would be a privilege, sir. Thank you so much.
Thank you.